Hello and welcome to the presentation with titled Application-Aware Software-Defined Flows of Workflow Ensembles. My name is George Papadimitriou and I'm a fourth-year PhD student at the University of Southern California. This work was done under the Dynamo project, which is funded by NSF and is a collaboration between RENCI, USC, UMass and the Rutgers University. Characteristics of today's computational science include data transfer and compute-intensive tasks, complex workflows, data repositories in sparse geographic locations, highly distributed compute locations, but the major challenge is the integration of cyber infrastructure to science workflows. A science application facing many of these challenges is the collaborative adaptive sensing for the atmosphere, also known as CASA. Traditional next-generation weather radars are high power and long range, but they have limited ability to observe effects in the lower part of the atmosphere. CASA has a network of short-range Doppler radars with adjustable sensing modes to respond to fast weather changes. These radars are suitable for near-ground weather events such as tornadoes, hail, or high winds. CASA has deployed a network of 7 Doppler radars around the Dallas-Fort Worth area due to the severe weather effects affecting the area and impact the community. CASA exposes complex network and compute requirements. Approximately 100 Mbps of raw data per radar are processed locally. 10 Mbps of downsampled moment data per radar are transferred to its data repositories and compute resources. 1 Mbps of radar products and images are transmitted to its monitoring dashboards. CASA transfers data to the DFW Radar Operations Center at NOAA Southern Region headquarters and also transfers data to the University of North Texas for collection and further processing. Two examples of the moment radar data collected by a single radar can be seen in this slide. On the left side there are reflectivity data and on the right side radar velocity data. In our previous work with Dynamo, we addressed many of these challenges CASA was facing by developing novel algorithms and mechanisms to optimize data flows across different national CI. As part of Dynamo, we introduced Mobius, a network-centric platform that provides an abstraction layer over the various resources. Mobius is capable of dynamic resource provisioning across Exogeny, Chameleon, Exceed, and other cloud providers. Additionally, data-aware workflow scheduling using the Pegasus workflow management system was provided, enabling CASA and other observational science communities to deploy and scale their computations to multi-clouds. On the left diagram, a scientist is defining their Pegasus workflow and the resource requirements, and the Mobius controller handles the provision of compute and network resources across the infrastructure. In the case of CASA, Dynamo enabled high-speed data movement via exogenous dedicated Layer 2 networks, provisioned compute resources to both Exogeny and Chameleon, and workflow instrumentation was done using Pegasus and HT Condor. However, we have identified areas the Dynamo system can be improved and optimized, offering additional value to its users. In our previous work, in order to provide isolation and performance guarantees, its workflows should use its own dedicated Layer 2 connection. Thus, sharing network resources fairly wasn't possible. Additionally, CASA's workflows have an event character, triggering workflow executions as new input files arrive, creating workflow ensembles. External scripts were used to create and submit new workflow tags, and there was no control over the workflow ensembles. Finally, monitoring the infrastructure in an easy and intuitive way was not possible. In order to address these issues, we have added services to the Dynamo system and we have extended others. We have extended the Pegasus Ensemble Manager to support the triggering functionality that CASA workflows require, and we have enhanced the network capability of Dynamo with virtual software exchange functionality. We have also incorporated the Prometheus monitoring system into Dynamo provisioned resources. Pegasus, via its Ensemble Manager service, can handle collections of related workflows. The Pegasus Ensemble Manager controls the number of workflows an ensemble can plan concurrently, and the number of workflows an ensemble can execute concurrently. As we said, the Pegasus Ensemble Manager now supports trigger-based workflow creation and execution. It monitors for new files matching a given pattern and generates new workflow DAGs based on user-defined workflow generation scripts. Each workflow ensemble can have its own configurations, and each of them can come with at most one trigger, adding new workflows to the ensemble. The virtual SDX functionality is provided through the Exoplex network architecture. An elastic slice controller called Plexus coordinates the dynamic network circuits and the broad security monitors. Traffic flow and routing are managed by a variant of the RYU SDN framework. A REST API is exposed to allow interactions with the SDX controller, and this is the one Mobius is using to interface and interact with the Plexus controller. Finally, the Prometheus monitoring system is deployed automatically with any Dynamo provisioned resources using Mobius. A Grafana dashboard gives insight to its nodes resources, such as CPU and RAM utilization, disk I/O, network I/O, and the file system. This provides a centralized view to all your project resources. To evaluate these new additions to Dynamo, and especially the effects of the new virtual SDX capabilities, we have created this deployment, which we use in order to execute Kaza's Wind and Nowcast workflows. In this deployment, the workflow submit node is one of Kaza's operational nodes that acts as a data repository. This node, located at the University of North Texas, connects via Stitchport to the HD Condor master node at UMass. The HD Condor master node connects to the virtual SDX slice that controls the data flow, which in turn creates the connection to the compute nodes located in Chameleon at TAC. Based on our previous work, we assigned 48 compute slots to the Wind workflow and 144 compute slots to the Nowcast computations. The compute node negotiation is done using HD Condor's matchmaking using tags advertised by the compute nodes. Finally, in order to apply network policies, the virtual SDX is targeting the individual network subnets of the computes, while all the states network have a capacity of 1 Gbps. The Pegasus Wind workflow, as can be seen on the left, has a variable size that depends on the number of input files. All input radar moment data files are unzipped, and the rest of the 4 tasks compute maximum observed wind speed, create contours with velocity threshold, and images. Finally, they also notify point of interest. These 4 tasks are executed with Singularity container that has a size of 163 megabytes. The test case data we use are 30 minutes of real weather data, and the individual file size is 12 megabytes, while the total size of the entire dataset is 6 gigabytes. The Pegasus Ensemble Manager is executing one workflow every minute. On the other hand, the Pegasus Nowcast workflow has 63 compute tasks. The first task splits the input data to 31 individual grids, and the rest of the 62 individual tasks compute reflectivity and contour images. All tasks are executed within a Singularity container that has a size of 153 megabytes, and the test case data we use are 30 minutes of real weather data with individual file size of 9.6 megabytes and a total size of 287 megabytes. The Pegasus Ensemble Manager is kickstarting one workflow every 1 minute. In order to understand the new virtual SDX capabilities, we first need to understand the network needs for each individual workflow. And in order to do this, we are measuring the network traffic during each workflow ensemble. For the Wind workflow ensemble, we can see that the total transfer of files is about 44 gigabytes, while the total runtime for the ensemble is about 2100 seconds. The average egress bandwidth on the data node is about 200 Mbps, while the peak bandwidth usage is about 250 Mbps. As we can see, the Wind workflow ensemble doesn't congest the network since we have a capacity of 1 Gbps. On the other hand, the Nowcast workflow ensemble during its execution transfers a total of 280 gigabytes, while the total runtime for the ensemble is about 3200 seconds. The average egress bandwidth is about 900 Mbps, and the peak egress bandwidth usage is about 960 Mbps. It's clear here that the Nowcast congests the network and it doesn't allow any other space for other transfers to happen while it's running. To evaluate the virtual SDX capabilities and test the new Dynamo features, we collect statistics from 900 workflow submissions and over 240,000 file transfers that generated over 900 gigabytes of network traffic. To evaluate the virtual SDX policies, we execute the Wind and Nowcast ensembles using 3 configurations. First, on a dedicated Gbps connection. Secondly, on the same shared 1 Gbps connection competing for the same resources. And in the third case, we apply network policies for each workflow ensemble, limiting the Wind workflow ensemble to 300 Mbps and the Nowcast workflow ensemble to 700 Mbps. These two graphs present the workflow makespans of each ensemble. On the left figure, we have the Wind workflows, and on the right figure, we have the Nowcast workflows. As we can see in the dedicated case, because the Wind workflow cannot congest the network, the performance is very stable and consistent. While in the Nowcast workflow case, this is not true. Workflow makespans range between 500 and 3300 seconds. Executing both workflow ensembles on a shared resource impacts the most the Wind workflows, increasing the median makespan by about 1000 seconds, while on the other hand, the Nowcast workflows are affected, but not by this much, only by about 300 seconds. Finally, by applying the network policies, we can observe that the Wind workflow's median makespan goes down to 400 seconds, and the workflows are now predictable again. However, limiting the network for the Nowcast workflow increases the median execution to 2000 seconds, but it doesn't affect it that much compared to its previous state when it had the dedicated connection. We have also collected statistics about the data transfer durations for each workflow ensemble. As it is expected, while executing the Wind ensemble on the dedicated link, transfers are fast and predictable, with a median transfer time of about 1 second. When we execute the Wind ensemble alongside the Nowcast ensemble, we can see that the transfer durations increase. For the Nowcast ensemble, this isn't true, since in both cases the network is congested and there is no change in data transfer duration times. Finally, after we introduce the virtual SDX quality of service policy, both ensembles see improvements in their data transfer durations. And even though we have less outlier transfers, the median transfer duration in both cases becomes higher than the 1 Gbps dedicated connection. To summarize, Dynamo is a multi-cloud platform with high-performance adaptive computing and networking support for science workflows. Dynamo enables automation and dynamic infrastructure management. By using the Pegasus Ensemble Manager, Dynamo now provides fine control over workflow ensembles, and with the new virtual SDX capabilities, it allows CASA scientists to use more efficiently their resources while maintaining the quality of service for their applications. Finally, introducing the Prometheus monitoring offers a lightweight and intuitive way to access resource utilization metrics from your web browser dashboard. This slide concludes this presentation, and I would like to thank you for attending, and I'm happy to answer any of your questions. Thank you.